Why should never happen? That's what I'm
All right, Caitlin, the exam is next week. Can you just confirm that you heard that?
Yep,
Caitlin?
I heard you.
Okay, great. The exam is next week. Don't miss it. Okay, guys, so today we're gonna continue with you can't see there. We're gonna continue with just building neural networks, right? So last week we did your first neural network, iris data set from beginning to end. We saw performance metrics. It was a classification type of a problem. This week we're going to look at the wine quality data set. With that is meant to be type of a classification problem, but it helps or a regression problem, but I can also turn it into a classification problem. And so what I like using that data set for both problems. All right, so that way I can show you the contrast between regression and classification in terms of the network and what you have to build. So we're going to go over that in a very similar way to what we did last week with iris. And, we're going to build from a very simple multi-layer perceptron to a deep neural network, as we've discussed in the theory, right? And after I would say after that point, we can start going at more complex neural networks, right? So basically, but that's the idea. So any questions? All right, I'll take a similar approach to what I did last time. I will download it from the GitHub and just run the code through the data and talk about it. And hopefully you guys are repeating this exercise on your own computers, either at home and ask questions if you have them, okay? All right, so as you know, here's the course website. I'm going to go to and I need to share the screen, sorry. Sharing the screen. So I'm gonna go my GitHub. And it should be under deep learning algorithms, second edition here. We're in chapter 4. If you remember, I gave you the website that you can go to. You can read through all that information. It's got a lot of the background and explanation, and ask questions about that if you have them. Last week, we looked at the iris CSV, and it was classification DL torch iris. That was your very first neural network. And we built, I believe, a deep neural network then, a 2-layer neural network, right? So, and then we saw the performance metrics for a classification type of a problem. Okay, today I'm going to focus on the wine quality data set, which is this one, CSV. And there should be 2 scripts this time around. One says regression and one says classification wine. All right, so these are the 2 that I will be going over. They're similar, but they're going to have some different things, obviously, because of the neural network is either geared towards a regression problem or a classification problem. And that's basically it. If time permits towards the end of these, then I'll just do some more linear algebra problems, right? As I said, I want to do those a few whenever we have time. at the end of class, okay, which is essential for going forward. And I anticipate by the end of today, if I finish, that I will give you a homework assignment that will be due after the exam, of course, because we have the exam next week, but it'll be something like this. I haven't really decided what it's going to be yet. Some data set and you building a neural network, right? Any questions? All right, so what we need to do is we're going to download the wine quality data set, just this one. So I'm going to go ahead and download it. All right, you can do the same. Then I'm going to go and I'll start with the regression part, which is this one. This is the Jupyter Notebook. You can just download it as well. Okay. All right, so I've downloaded both. Then, as usual, we're going to open up the terminal. Conda prompt. Okay. And I'm going to download. Well, actually, I'm going to move these files. ITS 520, 2024. I'm going to create a folder here called wine quality. Downloads, and I'm going to copy the data. This one. All right, here we are. Okay, so CD into desktop. Here we are. CD into ITS 520. PIR. Wine quality. Okay. All right, so we've got there the Jupyter that we're going to go through and the data set, basically. And we'll look at both. Let me just look at the environment, Conda environment list. All right, so it should be Pi38 that activate Pi38 ML 2024. All right, so Jupyter Notebook. All right, so here we are. Let's take a look at the data again, just briefly. So the wine quality data, it's got, I think, 11 features. They basically relate to fixed acidity, volatile acidity, citric acid, etc. So it's basically wines, right? So somebody took some wines, they measure some things like pH balance, etc. And then you're supposed to be able to predict the quality from 1 to 10, the rating. So is it a 6 or a 5 or and then we have measurements for it. So in the CSV, it's not so easy to visualize everything. Right? There seems to be a lot of samples also, and they seem to be separated by semicolon, not comma. So all these things we want to like check in the Jupyter itself first, get a feel for it, and then we're going to start processing the data to our X and Y until we can basically start training our neural network. All right, so that's kind of the idea. I'm not really saying that this is a problem that you should solve with classification or regression. It's really whatever the results are at the end of the day. But I like using this one to show you like the slight differences because it's the same data, exactly the same data set, but we're just treating the problem in two different ways. Okay, so I have it here. So I'm going to go over, I'm going to double click on my Jupyter. And now, basically, here we are. So, this is how you got it from the GitHub. So it's got the data. I'm going to reset it. I'm going to refresh the kernel. Okay. Okay. So let's load, as usual, we're going to load the libraries first. And after that, we're going to load the data set with pandas and kind of visualize aspects of the data set. And then from there, we're going to make decisions as to how we can train a model for it, for instance. All right, so I'm going to do, well, let's do it again. Okay. I think that was the. Okay. All right, so I'm going to hit run. So notice NumPy, Torch, Pandas, sklearn. All right, so those should be available. We're already installed. It's the same environment I've been using all semester. All right, then matplotlib mxl extend, which allows you to visualize things a little bit better. sklearn metrics. So today for regression problems, we're going to learn to look at a couple more metrics that we can look at that are common in machine learning for regression problems. I'm going to comment that out since I'm not going to use these. All right, so let's do this one. Okay. The parameters, as I said, the batch size, because we give several samples of data at the same time to the model, both to train and to test. The learning rate, it's going to be 0.005 or 0.001. You can play with that parameter, and it's basically how it learns. We're going to, at some point, drill down a little bit more deeply, probably before the exam. I'll do just a lecture on these terms. And epochs is the number of times we're going to feed all the data to the model. And epsilon is just a little parameter, so we don't have 0 by 1 issue or division by 0 issues. All right, so the parameters are fine. All right, now we're going to load the data set, wine quality. So read CSV, we're going to use pandas for that. We're going to tell it that the delimiter is semicolon instead of a comma, as we usually do. It's because that's the data set. Then I usually like to print the data set as it's a panda. Okay. Oh, it's in data. All right, so just I put them in the same folder, so just remove that path. Okay, and then now, there we go. So now we have some information about our data set. We have 4,898 rows, so that should be the number of samples. and we have 12 columns. The last column, quality, that's going to be our Y, the thing that we're going to be predicting, either as a regression value or a classification value. And then the features are going to be fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH, sulfates, and alcohol. All right. And basically people are rating it based on quality, what they think the wine is like. And you can see the values are in different scales. So these are in, 7, 6. These are in from, it seems to be 0 and 1, between 0 and 1, and so on. So these should be normalized. All right. And this should be something that is in the code here. All right. Once I have that, I can print out the header list. So these are the variable names, the column names. Okay. And then if you want to visualize just a few of them in a correlation matrix, you can just assign a second header list, which is, smaller. Notice that you specify in the column names the headers list, so you can that's just a way. I'll display all of them. So I'll do the correlation matrix again. These are just things I kind of do all the time, just to get a feel for the data a little bit. Okay. So you can see here the correlation between all the different variables. So I guess the most yellow variable here, the quality, is possibly this one, alcohol, seems to be one of the more important ones, right? In relation to the quality. You guys see that? So that's basically what this is telling you, kind of the importance of the variables. Any questions on that? All right. Let's keep going then. So now that the data, the thing with building neural networks in PyTorch, et cetera, is to we have to switch from data types. The neural network accepts only PyTorch constructs. Currently, we have a pandas data frame, so I'm going to convert it to, I could convert it directly to Torch, but in this case, I'm going to convert it to NumPy, basically. Okay, so I'm going to go ahead and do that. And I just converted the data. So now you can see the columns are gone. I only have the data in there, but it's basically the same data. You can print the shape, 4,898 by 12. And so we have one single matrix right now. We need to slice it basically so that we have two matrices, or two tensors, I should say, the X and the Y. So that's the next step. So wine raw data. So here I'm going to slice it basically, and I'm going to say all the rows by using this column here. And then here I'm basically saying all but the last one for the columns, okay? And in this case, I'm saying here I'm saying all the rows, but I'm saying the opposite of up here. I'm just saying actually only the last column, okay? Only the last column. There's a couple of ways of doing this, but this way, if I remember correctly, gives you tensors that are I, j. So that should be what we want. So I can print out Y here just to kind of look at the data that it is correct. The quick inspection you can see is pretty much the same thing as there. So that tells us that we got it correctly. And I always suggest printing the shapes. You can see it does give you, instead of giving you like just 4898, which you can with some slicing methods, this one gives you 4898, 1, which is what you really want for the shapes to be correct in the neural network. All right, remember that those are related to the matrix multiplications that will happen on the GPU, for instance. So you always want to make sure that you're anticipating that and that your code works for both CPU and GPU. All right, so you can see now we have 4,898 by 11. So that's the X and the features, and then 4,898 by 1. And that is the values, basically, the rating for each sample. So I'm going to go ahead now. I call this one my poor man's cross-validation. And the reason why I've said this is like by using this random seed usually when you're doing machine learning, you're going to run your code multiple times for whatever reason. So every time you're doing this, you're going to randomize the data differently. So it's at the end of the day, if you run this 10 times and you look at the performance, you kind of did a poor man's cross-validation, because you saw different performance metrics that kind of average out to something, at least visually. All right, so I'm gonna do, if you don't want that, you can just hard code this to something like 42, etc. All right, so I'm gonna run this to train test split. This was the sklearn function we used before, and that just gives us our 4 data sets now, X train, Y train. Remember, we trained the model on that. And then once the model is trained, we're gonna evaluate on X test, Y test. All right. We're doing a regression in this problem, remember? So the performance metrics will be MSE or family of MSE and R square as the metrics that we're going to use in this example. R square is strongly used theoretically in linear regression. In neural networks, it's a little bit less, I wouldn't say as it's less of a perfect fit than in linear regression, but it's still heavily used. All right, so you can, if you're comparing one thing to the other, at least, it's useful. All right, so here you can see now I've split the data. So it seems we're going to have 3,918 samples for training and 980 samples for testing. Any questions so far? Okay. All right, the data type, you can also print it. You can see it's float 64. In essence, you don't need float 64. You can switch it to float 32. I've had issues where I had errors with this, so I just like float 32. So I'm going to go ahead and change the data type. This is still in the NumPy structures, so I'm just changing them to float 32. And I'm not going to print that the data type has changed, but you can confirm it, and it should have changed. So now we're going to go ahead and take our NumPys and load them into torch.from from NumPy to create the equivalent tensor. So remember that the neural network does not take anything that isn't a torch tensor. So it's going to reject that. All right. So now, in the past, in the previous example, I think last week, I did not use these functions, right? I calculated the mean and the standard deviation. But this time around, we will use them. Okay, and basically you want to normalize your data, right? So basically the idea of normalizing the data is to have a feature in the scale from 0 to 1 and another feature in the scale from 0 to 1,000. You want to normalize them so that, or standardize them so that they're all on the same scale. Standardization usually puts them like -2 to +2, somewhere around that range. And then normalization puts it 0 to 1. So in this case, I think in general, people say that standardization is slightly better. So I have a tendency to always go with standardization, which is, you'll see the implementation here, basically. Okay, remember, so we're going to take we only do this on the X train data because the X test data is something you would not be able to look at, right? So you would only train on the train set, look at the train set. So here I take X train and Y train, basically. Sorry, X train, only X train. And I'm going to calculate the mean and the standard deviation of X train. And that's what I'm going to use in the equation for the standardization. So it's like we're going to grab the X and we're going to say X minus X means plus X standard deviations. You'll see the equation in a sec, and that basically does the standardization. So if we want to print X means, we can see it should be X means dot shape so it's 1 by 11. We know there's 11 features in X, so it's just one, like we take across all 4,000 or so, right? We calculate the mean of each of the 11. That's why this gives us 1 by 11. And the X deviation should be exactly the same. So we can also do that. And then for every row, we're gonna basically take the original row and perform the operation so that we normalize every value, every column. So this one is X deviations dot shape. And you can see it's 1 by 11 as well. Okay, any questions on that? So these are the normalization. Now we can create our train DS and our data loader for train DL, just like we did before. We take X train TR and Y train TR using a tensor data set. And then we're going to load that, which is now train DS, into a data loader. And we're going to specify the batch size, which I think was 16. And we're going to say that we want to shuffle it. So remember, every time we feed the data into the neural network, the data is shuffled, right? And that's something that we want to do. So I'm going to go ahead and run this. And we print train DL, and it is now a, yeah, go ahead. Yeah. Yes. It's better to do it. It's recommended to do it. Why is that? It's probably because you're averting patterns. Randomization does that, right? So it's, you don't always want to give it, you don't want to give it the data once, because the neural network then might pick up on something that's going on. Like the numbers always appear like this. I see this followed by that. So the next time it's still the same set of samples, but they're just randomized. And remember that then we grab batches of them. So we don't give the whole data set to the network. We just grab like a little batch, then a little batch, then a little batch. So just to give you an example, I'm training this board and that's the model. And I just grab like you guys over there and I give it. And then I grab you guys over here and give it. And then I grab you guys over here and give it. And I do that 1,000 times, right? So then let's just say, for the sake of argument, the model always picks up that in the beginning, there's always, 4 girls in the background. Do you see what I'm saying? For whatever reason, it just like picked up on that. But if I randomize it the next time around, I start with this batch. And this batch has, well, okay, almost 4, but 3 girls in the background. And the next time around, okay, those 2 guys over there in the background, you see that? So at every one of the 1,000 epochs, right, it's a little bit different. And that's as far as I can take it. I don't know any, that's what's happening. So the model gets the weights are adjusted based on seeing that. And so you kind of want to give it the data multiple times. And the best analogy I can give you is, remember what I said this a week ago, if there's a line right there, like a pipe or whatever, and a kid trips on it, that's all that kid needs to learn, okay, I'm not going to trip again, right? But a neural network with this thing of the epochs would need to trip on that pipe 1,000 times. And then after 1,000 times, it's like, I better not trip on that thing. It takes longer for it to train. That's one thing. And then the shuffling is the other example I gave you. Does that make sense? Yeah. So yeah, so yeah, that's what's happening there. All right, so we have the data, as you can see, we have the data here. And then now what I'm going to do is I'm going to start looking at architecture, right? So we've already looked at this. I'm going to build, this is a regression model. Okay, so it's going to be a regression model. So we're going to think how the architecture works for this one. So I'll do a regression model that is linear, a regression model that is multi-layer perceptron, and a regression model that is a deep neural network. Oh, and I also have a linear plus nonlinear regression model. All right, so 4 different models and architectures. I may need to bring out the whiteboard again for this one. So, yeah. All right, so we're going to do this one first. Yeah, let me just get the board. I always forget this point. All right, so we're gonna think of the first architecture, right? So remember, this is the way that we're gonna write it in code, and then I'm gonna kind of draw the diagram of what it would look like as a neural network, you know, as we represent neural networks usually. All right, so let's take a look at this one. So this linear regression model is a class, lin regression, right? This class inherits an N module, which is the torch, a way of the construct for building neural networks. It's got the two functions that we always use, init and forward. Okay. When we initialize the constructor, we're going to pass x means and x deviations. Why? Because we want to normalize the data as it comes into the neural network. Okay. We don't need to normalize the outputs, only the inputs in this scenario. So I initialize x means and x deviations. And remember that NN linear we discussed is basically the equation that we know y equal wx plus b, right? Where w and x, you know, and b are vectors of all the inputs. So here the architecture is pretty straightforward, NN linear, and we're saying basically that the input is 11 because we have 11 features, and in this case the output is just 1 because we're going to predict one number, right? A regression value, right? Which is going to be a 3 or a 5. In theory, we have a scale from 1 to 10, right? So it'd be a 1 or a 10. It just depends on the data that we have. But that's what we're going for. Okay, so we first initialize these parameters, then we create the neural network. So if you notice, the function forward is where we actually bring together all the pieces from here to build a neural network, right? So X goes in, that's the input. And so it's going to go through these 1, 2, 3 lines of code, basically. So what do we do? So here is the standardization, by the way, right? So this is, you know, pound sign. Here we standardize the data, right? Which is one of the techniques in normalization, okay? Or scale, or however you want to call it. So what do we do? If you notice, it is basically the equation is this: x minus means divided by deviations. Do you guys see that? That's it. Does that make sense? That's it, okay? You can use some fancy functions sometimes, but it's literally doing this. All right, so then what do? We take the x's, which is going to be, let's say, 3,000 by 11 minus 1 by 11. Why does that work? Because we're going to broadcast that means to all the samples, okay? And then we can do the computation, okay? So basically that's what's going on there. As an exercise, I encourage you guys to try that operation on your own. But this is one of the operations in the linear algebra problems that I gave you. Okay, and then once we have that, we're going to divide it by x deviations, basically the result of that. And then at that point, your data is scaled, basically, and you can look at it. Does that make sense? All right, so that's done. So once the data is processed like that, what does that mean? Now the data, we no longer would have things that are 0.23 and something that's 2000, for instance, right? Everything would be in the same scale between, let's say, like -1 and +1, somewhere in there. All right. Now that we have that, the x processed, then this x is now the scaled x, and then it would go into the linear function. So that linear function is the neural network, which in this case is a very simple linear regression model. It's a linear model. It's not deep and it doesn't have any activation functions. Therefore, it doesn't have the power that a neural network should have, right? It's only a linear model and nothing else. Okay. So once it goes through that, you get basically the predictions, and that is basically this result here. Okay. So let's think about this neural network graphically. So I'm going to go ahead and go to the whiteboard. Let's remember what that looks like. Just give me a sec. The battery's not charging. Right. Okay. So the neural network here for this regression should look like the following. So it's 11 by 1. So that basically means it only has we're only defining an input and an output and then nothing else. So here I'm going to do ... until here, but there's basically 11 inputs, right? So it's a neural network with 11 nodes at the beginning and then 1 node at the end, at the output, and there's no hidden layers in between. Okay, does that make sense? That's a linear regression basically, and it's linear, not an actual neural network because it doesn't have any activation functions and it doesn't have any other layers in between, which are needed for it to be a proper neural network. Any questions on that? All right. So anyway, that's the architecture and it's fully connected, right? Remember, I can't draw all the connections because it would take a long time, but it's a fully connected. Most of our networks are. All right, so that's the first one, architecture. So we can exit out of here. Share the screen. All right, so that's our first one. I'm going to go ahead and run it. Okay, and then I'm going to skip the other ones. I'll come back to them as we start defining it. So I can skip this class and this class and this class, and I'm just going to come back to them. All right, so the next step is I'm going to now do a training loop. All right, so this training loop is basically has the 2 for loops, right? So we're going to do for epoch in range and epochs. So this is where I'm going to just give it all the data 1,000 times. This is where the shuffling happens and everything. Then after that, I have my train data loader. So I'm just going to grab XB and YB. So why do because the batches are of size 16, I'm grabbing 16 by 11 in XB and 16 by 1 in YB. Does that make sense, guys? I encourage you to print the shapes of these, right? And look at it. That's always a really good idea. So you can do something like, you know, when you're writing things, it's helpful to do this. You have to do it in a print statement. You have to do like print X shape and print YB dot shape, and then put an input just to halt the program so that you can actually see those, and then you can get rid of it, okay? Just to see the shapes. Once that's done, you give XB to the model, the neural network. Remember, the weights are pretty bad at the beginning. In fact, they're random. That's going to predict a Y pred, and that Y pred and the YB are going to be sent to the loss function, which in this case is going to be MSE, basically, mean squared errors. And all that equation does is it compares basically, you know, a predicted value. So you'll have like 3 and 2.5. And you take the difference of those two, and basically it performs an operation to calculate that difference, right? And that difference is going to be captured in loss. That information is going to be used by the neural network to update the weights, okay? And that's something called stochastic gradient descent. We'll touch on that algorithm a little bit later on some of the intuition of that. But for now, you always just use these 3 statements. If you notice, op 0, 0 grad, you take a loss dot backward, which basically calculates a parameter, whether you're going to add or subtract to the weights. And then basically you take the step where you actually add or subtract to the weights, right? And you basically modify it. This part of the code is just printing the loss every 20 epochs or so, just to see what's going on, okay? This is something that we did before. It's actually this we'll do all the time. This is the basic operation to train the neural net. So here we define the function. And then now, if you notice, that's it. So at this point, we're able to train the model. I'm going to use the first one. So linregnet. So linear regression net. So I'm going to comment this one out. Or I uncommented actually, and I'm going to comment out this one. So I'm using that one 11 by 1. That's it. I'm using that model. Then I'm instantiating the optimizer, which is the thing that actually does the calculations. So I'm going to do torch optim dot atom. I'm going to tie the model parameters, which are the weights basically and the biases, to it. And I'm going to specify or hard code the learning rate. You see that here. Opt, and then I'm going to also define the loss function, the thing that like the equation that I'm using to compare the real to the predicted, right, which is that one. And then I pass all those parameters over here to the function we had discussed initially, right? So if you notice, everything is tied together. So now I'm going to go ahead and hit run. And there, oh yeah, well, okay. I did put that input in there just to show you guys that it's 16 by 11 and 16 by 1. Do you see that? So it's grabbing a batch of 16 features and then the predicted value. So I'll kill this and I'll remove that and then run it again. Okay. So this is what I added. I'm just going to get rid of that. Okay. So I'm going to repeat this. Right, and then we should let it train. So remember, the objective is for this loss to go down. Okay, so that's the objective always. So it's starting to go down basically. And it's usually in the very first iterations, you see like the big jump, and then it's a little bit harder over time. How many epochs did I say for this? 100, right? Yeah, it's 100, so that's not too bad. Okay, it's already at 80. It's almost done. And the loss has gone down to about 0.30. We have normalized the data, which is good. All right, it finished. Okay, now we want to evaluate the model. And what we're going to do is we're going to basically, now the model is trained, right? So the model has weights, good weights. Okay, so what do we do now? We want to give it the X test TR data. So we're going to look at that. I'm going to add a cell here. I'm going to do X test TR dot shape. And this is 980 by 11. So it's going to return 980 by 1. And we need to compare that to the Y test TR, basically, to see how well it performs, okay? That's the idea. So I'm going to first generate Y-pred test. The shape of it is 980 by 1, as you can see. And then here I have this from sklearn, this R square score. And you have to take, currently, Y-pred test is a torch tensor. So we're going to convert it into a NumPy tensor, okay? So in this case, that's why I'm taking Y-pred test. You can see that here. You have this parameter called detach, because sometimes you get this error from PyTorch that says something like you can't process something that's tied to the graph. And so the detach allows you to literally like remove it from the graph. And then after you do that, you still need to take it, convert it to NumPy, basically. And then I do the same with Y test TR. So these are the act, like you could call it the labels of the test set, right? And so we're going to predict it, basically. So here I give it the real and the pred, basically. And it gives us an R square of about 0.29. And that's your R square. R square, you know, you probably, if you've taken a statistics class, you've heard that it's a value between 0 and 1. 1 being the great good value, really good, 0 being pretty bad. Keep in mind, R square in sklearn can give you negative values, and that just means your model is having a hard time understanding. There's other reasons why that can happen. 0.29 is not especially great, but, you know, it's not my goal to get 1% here, you know, 100%. It's just to show you. Now, how is this useful, this value 0.29? It's useful in respect to me using the other 3 architectures, right? So I'm going to try MLP. I'm going to try the deep neural network approach. Hopefully those would be better. How will I know if they're better? Their R square should be higher than this. Does that make sense? And then I would go with that effectively. Okay? So I've calculated this. Now I'm going to go ahead and print the shapes, just because, and then I can print that as well. Now this function I sometimes like to use, and it's basically just printing out the real value and the predicted value for all 980. And the point of it is just to look at it. Just look at it, analyze it, see if you're happy with the results. So I'm going to go ahead and run it. And you can see, for instance, what this means is that the predicted was 5.7 and the real was 6. So I would say that's close enough. 562 to 7, okay, not as close. 5.7 to 6, 5.9 to 5, and so on. You get the idea. Any questions, guys? Making sense? Yeah. So that's it. I mean, so I'm not going to do anything with deploying models this class, so I'm going to take that out. I'm not going to use XGBoost. That's just in there for comparison. All right. So, all right. So that you've completed your first regression. You've done a linear regression with a wine quality data set. Okay. Make sense? Now, what I'm going to do is I'm going to repeat this 3 more times. And the only thing I'm going to change is the architecture. All right. So I'm going to try other architectures now. So I'm going to go ahead and go to whoops. Okay, now I'm going to repeat this exercise, but I'm going to use a different architecture. So I'm going to use multi-layer perceptron, right? So this one. So when you talk about neural networks, you know, basically that this is it, right? So you're trying, you know, ever more complex architecture. So we did a linear regression. Now I'm going to do this multi-layer perceptron. Let's talk about this class. So we, you know, again, we provide NN module. We have the 2 functions, the init function and the forward function, right? This is the constructor. This is where we build the architecture. We pass to it X means and X deviations. You can see that here, just like we did before. And the thing that's going to change this time around is that we have more layers, and we need to define those here. So now I have linear 1, linear 2, right? So basically that means I'm going to have one first layer that's going to be from 11 to 8 with an activation function called sigmoid, okay, which will process the values. Then I'm going to create another layer from 8 to 1. So if you notice, the input is 11 still, and the output is still 1. But what's in between is a new hidden layer of 8. So remember that, you know, this value and this value need to match, basically. And then we can use something called dropout, right? Which I will describe as well, but it's a way of dropping connections, basically, okay? So that in this case, a dropout with a rate of 0.2. All right, so we've defined these parameters. Now let's go ahead and build a neural network. So as you can see, it starts with X. X goes in, and you standardize the data, basically. So X minus X means divided by X deviations, just like we calculated this before, okay? Then, first thing is X goes into the first layer. It goes in as 11, and it gets, the vectors go in of size 11, and they get transformed into vectors of size 8, okay? That vector of size 8 that comes out of here then goes through an activation function, and that activation function converts the values to a scale between 0 and 1, because that is the signal, right? So regardless of what they were before, they get mapped into a scale from 0 to 1. Then that vector comes out, it's still size 11, sorry, size 8. And now it's going to go, oh, it goes into a dropout now. And dropout basically is this idea that you had a fully connected network where some connections are dropped randomly. And you train the model like that. And I'll discuss that a little bit more once we're in the whiteboard. And then once that X comes out, it goes into linear 2. And linear 2 takes that vector of size 8 and maps it into one neuron of size 1. And that's it. That's the prediction. That prediction will be compared to the real value, right? And the weights will be optimized so that it learns to predict as well as possible. Once that's done, YPRED is returned, and that's the multi-layer perceptron neural network. This is a proper neural network, right? So let's take a look at this one on the whiteboard. Okay. So the neural network now has this layer, and that layer, right? So the last layer has one neuron. That's the output layer. This is the input layer, which has 11. And this one has how many? 8, exactly. That's the 8 that you see in the code. Hidden one. They're called hidden layers. Hidden one. The latent layer. But anyway, so this is hidden one, okay? And it's fully connected, right? So what that means is fully connected. Imagine there's 11 connections there. But there's 2 things that we've added this time that I didn't discuss the last time. One is dropout, and the other one is the sigmoid function. Okay, so dropout, let's talk about that one. Dropout is basically randomly, it will drop 20% of these connections. You see what I'm saying? So for instance, let's just say it drops that one. Do you see that? So in that particular iteration, it'll just drop that connection. It'll run the data through it and calculate the weights just for the things that are left. And then in the next iteration, it'll start with all the connections again. And then it's going to drop one randomly and train with them. Do you see that? So why do that? So this is something that was invented by Geoffrey Hinton. And basically the idea is actually very interesting. It's a way for you not to have to create 1,000 different architectures. Because if you think about it, you know, I could build a neural network that has, you know, let's say 100 neurons or 80 neurons or of specific things, right? Remember that this is happening at different scales. So basically what he's saying is like he's creating, you know, some neural networks of say 100 connections or 80 connections, etc., all at the same time. You're trying different combinations of them. So that's kind of the idea. And then, and that just forces the neural network probably to be more efficient. Okay. Any questions on that? Huh? Question? Yeah. I mean, that's basically the idea. So dropout is something that has worked really well. So it's recommended that you always try it. I mean, you know, you may see improvements or you may not see them, but that's the idea. You remove connections basically. All right. And you can add a dropout here and it'll happen there. And if you add a dropout there, it'll happen there, and just, you know, try it out. Okay. The second one is the activation function. And that basically, the way that you can write it is by writing it like that. So what that means is that sigmoid happens to all the values that come out of here. These 8 values might come out as, you know, in some scale. I don't know which scale they're going to come out in, but sigmoid is a function. Sigmoid is a function. So I'm trying to draw. There we go. Better. Okay, better. All right, and then let's go to pen. And then it should be between 0 and 1. This is minus infinity plus infinity. So whatever the values here are, which I don't think they're going to be in very high scales, but they might be in some. So let's say -10 to +10, all these values get mapped from the x-axis to the y-axis, basically, which is going to be, this should be like at 0.5. Sorry, it came out a little crooked, but it's like that. Does that make sense, guys? So it never quite touches 1 and never quite touches 0 here. And it's just like, sort of like that, like an S shape. But it's basically mapping the values from this scale to 0 to 1. Okay? And that's one of the activation functions that are available. There are other activation functions like ReLU, GeLU, etc. Give this one a shot. Yeah, a little bit more. All right, any questions? So these are the activation functions. This is, at some point, we'll look at these as well, more specifically, but I'm just introducing them right now. Okay, this is good. This is similar. This idea is similar to scaling and normalization, and this is what gives the neural networks the power that they have. Okay, so just to give you an analogy, because we've done this contrast. Although we're doing regression here, in the previous example, right, we could only do straight lines through the data. Okay, that's all the power that the network had. In the new example, we can start to build a more curvy thing. Do you see that? That's basically the difference. Okay, does that make sense? Guys, any questions on that? That's what neural networks do. And this is the example of a linear regression, and the example of classification. Right? It would be a similar idea. If it's not a neural network, then we could only do like straight lines. Right? That's what the architecture can create. Like it can just draw that. Whereas if you start adding a neural network, so obviously that's a better solver of our problem. Does this make sense? So that when you hear linear to nonlinear, that's basically what it means, okay? In whatever context you're looking at, you just have more power to understand the data. All right. So I think that explains, let's go back to the previous slide, slide 1. So we have built a multi-layer perceptron, I think, 11, 8 to 1, and that's for our regression. Okay. What time is it? All right, 6:12. So let's go ahead and run this architecture. Okay, so I'm going to do MLPNet now. And basically, I can ignore that for now. I'm going to do the train loop. Now this is to be MLPNet. Was it like that? Oh, underscore net. Okay. And we got to let it train, basically. So what do you guys think? Do you think it'll do better or worse? The reality is you don't know, right? You hope that a neural net will do better, but you just don't know. We are normalizing the data. We are using a neural network architecture, activation functions. Actually, the loss looks worse, right? You look at it. Now, keep in mind that neural networks have more, can sometimes have more parameters, this obviously has more weights, might need a few more epochs to do the calculations. But let's see how it comes out. How will I compare this to the other one? I'm going to use R square basically, right? And here R square is one of the ways that I can compare the performance. Okay, it finished. Okay, I'm just repeating the same thing I did before. So our previous score was 0.29. This one is 0.27, so actually lower. Didn't do as well. You guys see that? That's it. So just because you throw a neural network at something doesn't mean that it's just automatically going to give you better results, right? You got to work at it. Okay, add more things. And that's basically it. So I printed the R square. You can also print the values themselves, look at them just for corroborating things. But yeah, so 0.27 is where we're at. All right, it's 6:16. We have 4 minutes. So let's look at the next architecture. And then maybe I can leave it running. So the next one is a deep neural network. So hopefully it makes sense as well. This one has 2 layers. So right now you can see the same process. We have an init function and a forward function in the constructor or in the class, sorry. DLNet is this one, deep learning. Why is it deep learning? Because this one is going to have 2 hidden layers, hidden 1 and hidden 2. So notice we have our X means, X deviations, start at 11, transform the data to 10, then from 10 to 6, 6 to 1, and drop out, let's see that 0.25. Also notice that instead of using the sigmoid, I'm going to use this thing called a ReLU, which is called a rectified linear unit. This is another like sigmoid, but maps the data different. In fact, this one is pretty simple to understand. Transform the data from 0 to infinity. So what that means basically is any negative values are 0 and positive values just stay whatever they are. Do you guys see that? They're also known as the hockey stick graph. So let's go ahead and that's basically it. So you can see that here, our X goes into forward. X minus X means divided by X deviations gets standardized. So now we got X. X goes into linear 1. So that's 11. It transformed the vectors from 11 to size 10. Why 10? I just chose 10. You can change it to some other parameter, other value. Then the transformed vectors of size 11 go into the activation, which is a ReLU activation. So it's going to change all those values to now not have any negatives, just positives. Then that goes into linear 2. The transformed vectors of size 11 get further transformed into vectors of size 6. And then those vectors of size 6 come out here, which now go through another activation, which is also a ReLU hockey stick approach. And then finally, that goes into linear 3, which just takes the vectors of size 6 and maps it into one neuron of size 1. And that is the predicted value that gets compared to the real regression value. Any questions? All right, so let's go to the whiteboard again, kind of draw this out. So I'm gonna do here, oops. So it's gonna be 11. There are 2 hidden, and the last one is 1. Huh? In between, right? So yeah, I'll do that. So dot, 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 there's 11 here. There's 2 hidden layers in between. First one had what, 10? So 10 neurons. Dot, dot, dot. And then this one, I think, had 6. And draw all 6. They're fully connected. So remember, that means fully connected. If I had a dropout around here, I would just drop one of these connections or 2 of them, depending on the rate. And then remember, there's one more thing. The activation is now ReLU. So I kind of just wrap the thing around to indicate that after these outputs come out, they need to still go through that function, okay? And that's the ReLU activation, which stands for rectified linear unit. And it basically has a hockey stick kind of a shape. So it should be something like this. And then like that. You see that? That's why it's hockey stick. So minus infinity, any negative comes out as 0, right? And then this goes to infinity also. So then all the positives go through and the negatives do not go through. There's one called leaky ReLU, which, as you might imagine, just a little bit of what is on the negative side comes out, okay? But this is the standard ReLU. This has been found to be pretty good, by the way, in neural networks. For instance, LLMs, I was reading a paper the other day, and it says that tan-H is not to be used in LLMs, but, so, they all have different impacts in the neural networks, and it takes quite a bit of experimentation to figure these things out, right? They're less theoretical and more like out of thousands of papers, this is the trend that has been seen. Okay, any questions? All right, so that's the architecture of the neural network. Since it's almost 6:20, I'm just gonna start running it. So let me close here. Switch over. All right, so this was DLNet, right? So I'm gonna load it in memory. And I'll do that. All I have to do is change this to DLNet, and now I'm using that architecture instead of the other one, and I'm gonna just run it. All right, yeah, it's running, so it's 6:22. Let's take a 10-minute break until 6:32, and then we'll pick up here and finish up the class for today, okay? So, and I'll stop this video